All right, cutting that open, cutting that short, cutting that something. Where's my camera? It's disappeared. Why isn't it switching on? Ugh. What has disconnected? Give me 2 seconds, apologies. I've only just realized my camera's disconnected. What magic? It's plugged in here. This is plugged. Well, it is plugged in, but of course nothing's working. How's that? Nope. Goodbye, camera. It's been nice knowing you. Okay, how fantastic. Let's instead go to the other camera, which is not that good. All right, hi everyone. How's it going? Can you see me? Can you hear me? Amazing. Oh, amazing. The volume's too low. That's because who knows which microphone is now going through. How's that? Is that better? Okay, amazing. All right, so today we're going to have such a good time. We're going to do more linked lists. I hope you had a really nice break over the 4 days of the Easter long weekend. I hope you had some chocolate and some sleep. Those are the two most important things. Welcome back to week 8, stress less week, where you can pack and pat. Definitely don't pack an alpaca, but you can pat an alpaca, and then life is better. I think they've got puppies this week as well. There's puppies there as well, that's pretty exciting. I'd want to. Well, I always want to pat puppies. I am really struggling with language. Okay, here we go. So, linked list today. Because my camera is now a different camera, you're going to see me looking away a bit as I look to the main screen where the coding is on. So, anyway, whatever. Doesn't really matter. You're not here to see me. You're here to see the lecture. Okay, so welcome back. Hope you're all feeling good. Ish. Assignment 2 is there. I can see some of you are very nervous about assignment 2. Please don't be. Please feel free to ask, questions. Please feel free to, go to your labs, ask your tutor questions as well. They can help you as well. And they can help you, get started if you need to. We will also do I'll do a poll as well next week about what you want to focus on next week as well, if we're going to do something similar to the linked list assignment, or if we just go straight to like similar types of questions that you might have in the exam. This week in the lab, the check-off activity is actually going to be array types of questions that are similar to exam style questions. So, they are there so that you can get a good feel for what the array hurdles look like in the exam, and for, how long they take you, how you feel doing them. So they're a pretty good indication of what the array questions are going to be like. Amazing. Any questions so far? But the best part about this mini exam is that no marks are counted, right? It's really just for funsies and to give you the exposure to what it looks like in the final exam. Any other questions before we commence? Okay. Sophie, could you please do a poll about how we're all feeling about linked lists, just so that I can get a feel for where everyone is at? The final exam is not until May. This is just like a mini, all it is asking you 2 hurdle questions similar to the array hurdles and 2 debug questions as well, to give you an indication of what the exam will look like, but also to remind you to study. Yeah. Okay, I'm going to have a look at this lovely poll before we start, just so that I can get a feel for what we're doing, because the next poll, no, the next poll, Sophie, thank you so much, is going to be whether we're going to do one more inserting into a linked list and we go over it again, or if we just go straight to deleting. Thank you, Sophie. Thank you, Bella. I don't know which one of you is doing the polls. Oh my goodness, 41% are still feeling very confused. No, don't finish it yet. I'm not ready to finish it yet. Okay, well, it's finished. Why do you have assignment 2? Because there are 2 things that we want you to learn in programming fundamentals, and they are how to use arrays and how to do linked lists. So, and those are the 2 assignments, and they're also the 2 hurdles in the exam. Trust me, you might hate how linked lists are a hurdle, but you will thank us later when you're doing 1521. Yeah. Yeah. No, that's okay. That's okay. It's because I didn't really, I was just talking to you and then I was like, yeah, let's do another poll. All right, I'm going to let it get to 60 votes. But I think it's overwhelming. Yeah, let's insert into a list still. Okay, fantastic. Oh, don't cry. I swear it's not that bad. I really do feel like maths is worse. I don't know. Yeah. Okay, let's do a little insert into a linked list. You think maths is so kind compared to this? Wow, okay. Okay. That's well. I honestly now I feel like I've done some false advertising, but I swear in like another 1 week or 2, you'll be like, actually, linked lists is fantastic. So yeah, look, Bella, same. My also unbiased opinion is that 1511 is way better than any course you'll do. This is really as good as it gets. After this, it's it's all downhill. So just enjoy the ride. Okay. All right, I had some water. I'm ready to start. Let's see what's in these slides. So the reason there's no lecture 12 slides is because we didn't really move forward very much. Everything was in lecture 11. I did put up these slides this week, but we're not going to really, we will go through them in the second part of the lecture, not in the first. So last time I sort of stuffed you full of information. No, I'm not going to make some lame dad joke about glue. There was a lot of glue though, so that did not help. So we did multi-file projects, and our linked list is also like a multi-file, and so is your assignment. Then we did linked lists. We created a list, we inserted some nodes at the head of the list, we traversed a list, and we inserted nodes at the tail of the list. So today what I want to do is insert a node at some sort of position anywhere. And then what I want to do is to delete some nodes in the list. And then we'll talk about where we're going to delete, at the head, at the tail, in the middle. If there's only one, item in the list, what if it's an empty list? We're just going to talk it through, see what's there, and go from there. Okay, where's the code today? I've moved all the code we did in week 7 into week 8 so that we can, we can just keep updating the same chunk of code, but the copy is still in week 7 as well. So we've got in week 8 now is also code. I'm going to come out of this now, and I'm now going to go to our code, which is amazing. It's everything you've ever wanted and needed and didn't know you had. Okay, excellent. I'm just going to check. Okay, we can finish the... Oh, someone's saying physics is the worst. Someone's doing computer engineering, I can tell. Yeah, I remember doing physics. I agree. Not my favorite subject. Okay, back to this. Why am I'm getting on tangentials all the time. Tangents everywhere. So let's go through what we had already, what we've drawn out, and then we can continue and we'll do insert at any position. I might do the code for insert at any position. We'll talk through it, and then we'll kind of move from there. I know that quite a few of you, I read all your feedback. Thank you so much for leaving me the feedback. I know that a few of you are struggling to keep up with the pace. So I will try and slow it down as much as possible. I would love for you to leave me some feedback again, whether you want me to slow it down a little bit more. There are things that I have to cover today, which is why I might speed up a little bit and then slow it down again. Next week, I will slow it right down, okay? So we will go over things, we will reinforce things, so don't worry about that. Okay, so let's get started. Am I teaching 1521? No, even though I love MIPSy. Okay, this is our main. So what I would like to do is I would like to do a function, which we're going to do now, and that function is going to be to insert a node at any position, okay? So we're going to work through that. So we want a function, so what I'll do is I'll go in here and I'm going to enter my header file, so my .h file, and I'm going to say now that I want a function, okay, that will insert at we'll insert a node at any specific position in the linked list. Okay, so what that means is that I have a linked list, and in that linked list, let's say I've got so in that linked list, let's say I've got something that looks like this. So I've got this linked list, and let's say I want to insert at position 2, okay? So, I mean, it depends where we start counting, but let's say this is position 1, this is position 2, and I want to insert after this node in here, okay? So what steps would I take to insert this node? First of all, let's say I want to insert node 7 at position 2. That means it would have to go into position 2. Let's do after position 2. Okay, so if I want to insert after position 2, then what I will do is I'll count my positions. So 1, 2, which means I want to insert this node in here. So the first thing I'll need to do is I'll need to create this node with 7 and null, yeah, so an empty node. And what I will do then is I want this next to point to my new node, and my new node to point to whatever the next was in that position 2. So then that will break that, and what I'll have is I'll have this kind of little loop that connects up my nodes in a different way. Okay, so who said that? Well, there's other courses that I teach. Maybe as you I teach some 4th year courses, the last ones that you do. This is my only intro course that I teach. Okay, so let's see what we would do to actually create that. So if we were to do some inputs and some outputs into this function, and this function is inserting a node at any specific position in the linked list. So what do you think I need as my input into the function, and what will be my output out of this function? So this, like what we're working on now, is different ways of inserting nodes into a linked list, and then we will do basic ways to delete nodes out of a linked list. And then it might change a little bit based on the context of what the question is asking. But this is the basic code that you will need. Okay, so great. So what we're going to need is we're definitely going to need an int position, some sort of where are we actually going to make this insertion, and the node that I want to insert. Yeah, so the value of the node that I want to insert. Great. And I need to give it one more thing, I think, for it to be all good. So I need to give it the position. I need to give it what I want it to insert. So position, what I want it to insert, and yeah, the head node, the list itself. So if I want to give it the list itself, that means I give it the head node, yeah? Because the head node allows me to give it the start of the list, which basically allows me to have access to the whole list. Because if I know where the head of the list is, then I can follow it through each and every node to the end of the list, and that means that I've got the access to the whole list as well. And what do you think will be the output of this kind of function? So someone's saying void, someone's saying nothing, address, head node. Okay, so what if the list is empty and I'm inserting at position 1 the very first node? Okay, so what does that mean I would need to return? Even if the list is not empty and I want to insert at position 1, the very first position. That means what's going to change in that list if I'm inserting at the very first position? So if I had to insert this node, but I had to insert it over here before this one, that means the head will change, and that means that I will lose that node and the link to the next node because I won't have updated it. So what I need to output out of this function is the head of the list in case that head of the list has changed, okay? So we want to output the head of the list in case the head of the list has changed, i.e. we have inserted at the head, okay? Otherwise, we would lose the list or the very first element of that list. Okay, this is like intense. I'm writing an essay in here. But hopefully when you go back to it, you can look at it and you can see, and it will remind you of things. Okay, great. So that means our definition will look like this. So we're returning a struct node pointer. So that means we're returning a pointer to a node of the linked list. And then we're going to call it insert at. And we're going to give it the data. We're going to give it the position, and we're going to give it the head of the list into which we want to insert. Great. So now we have our definition. I'll save that and I'll go down here and we will actually implement this function. Yep. Does that sound good? Okay. So as we talked about here, the very first thing that I do is I'm going to need to keep track of the position in the linked list, but also I don't have a node yet to insert, right? The node has to be created first. So the very first thing I'm going to do is I'm going to make this. So I'm going to create this node over here to actually then do the insertion. So before I start counting my position, before I start actually manipulating anything, the first thing I'm going to do is I'm going to create the node. Okay, great. So the first thing I'm going to do is create the node. So I'm going to create a pointer to a new node. Okay, it's going to be called new node. So the struct node pointer just means that I'm creating a pointer to something that looks like this, to a struct node. So the node is going to have some data and also this pointer to the next node. And that's what makes it a linked list, in that it's got the address of the next node that you can follow through. Okay, so what I've created here is I've created a pointer, right? Just a variable pointer. But now what I'm going to do is I'm going to call my function that I have already got, which is create node, and I'm going to give it the data that I wanted to create with. So I'm going to give it data, and let's have a look what it looks like. So our create node here is data, and it's going to have the next. So I'm just going to send it with null. So what this will do is it will call this function that we've already written over here, and it will call it with this 7 and a null, because let's say I'm going to insert a 7 and a null in this case, in this example. But it's using this data and it's using the null as just, so what this code does is it creates the node that I'm going to then insert. Okay, so when I insert into a node, so when I insert a node into a, when I insert a node into a linked list, what are some things that I have to think about? Okay, so what are things that you should always think about when you're inserting a node into a linked list? What are some special cases that you should always consider, just like besides the normal case, besides writing the code, what should you always think about when you're kind of testing your code and seeing if it works from a specific angle? Yeah, so really good. Always think what happens if you're inserting at the head of the list. And the reason this is important is because the head will change, right? And once the head changes, we need to make sure that we're sending the right thing back, and so on and so forth. Index is out of bounds. It could be that the position that we're inserting into is out of bounds. So position is out of bounds. This could be, for the time being, let's assume it's going to be always correct. So for the time being, let's assume this is always valid, but absolutely, in the real world, you would have to consider that, absolutely. And what else do you think we should always consider? So set at the tail, I agree. The other thing you should always think about is inserting into an empty list. Okay, so always think about that, because the head will change. Same as above, yeah? Okay, great. Excellent. So this piece of code here has created the node for us. So now we need to do some magic. So before I start considering the edge cases, I'm going to do it for the standard case, as though we've got a whole list of things going on. Then, or we've just talked about the edge cases. Why don't we look at the edge cases first? Okay, so two edge cases are, what happens if that list is empty? Okay, how will I check for that? How will I check? So an edge case is basically anything that's outside of the normal standard thing. So like over here, when I said I insert just over here, that's kind of the standard case. Edge case is anything that might happen that is outside of the like normal thing that can happen. Anything that's like slightly special, basically. Okay, so what do we reckon? Yep, so the first thing we're going to check if the head is equal to null. So what this is checking for is if the list is empty. Yeah? So if the list is empty, then we're going to do okay, so that's checking if the list is empty, this one over here. I would also like to, at the same time, because both of these, inserting at the head of the list and let's just do if the head is null, and then otherwise I'm trying to do too many things at once and it might get confusing. Okay, so if the list is empty, so let's say if we have a situation where okay, so I've got nothing going on. So all that I'm doing is I've created this node. Let's say it's got 7 and it's got null. And I want this node now, if the head is null, I want this node to become the new head. So what do you think I would do now? So what do we reckon? Who's with me? Who's lost me? So if head is equal to null and the head is this thing given here, then all I have to do is really return this new node that I've given. Yeah? Because the data was already, I've created the node. So now I'm just saying, okay, if head is equal to null, this is going to be the new head of the list. Yeah? So I'm just going to return this new node, and I'm returning a pointer to a struct node, which is what I'm doing. So that's my new head, that means. Yeah? How is that? How is this little chunk here? Is this okay for now? We haven't checked for the position. No, we haven't even started to do the position. So for the time being, we're going to leave the position. We're going to assume the position is correct. Okay, we're going to assume it's valid. And then we're going to come back to it and change it. Or perhaps you will when you play around with different things. Okay, great. Else, we're going to have to keep track of the position. So we're going to have some sort of position counter. And I'm going to set it to 1 to start with, only because I'm assuming that this is position 1. So I'm going to start counting it at 1, okay? And or I can count it at 0, but we can check that, right? Off by 1, that would just be a little logic error, and I can see what happens when I run it and if it's going to mess up what I want to be doing. Okay, then I want to have a node that I'm going to use to move through my list, okay? So once again, what I'm going to do is I'm going to have a pointer called current, and I'm going to set it to the address in head, okay? So that will allow me to traverse my linked list without changing the head ever and never touching the head of the list, right? Because all it is, I'm still modifying it at the source because I've got the addresses, but it means that the address stored inside the head is not changed, okay, until I want it changed. So I don't by accident lose my list somewhere, by complete fluke. Okay, great. So now I have some sort of counter that's counting how many nodes I have, and I have a current which I'm going to use to traverse through my list. Okay, so great. Now I'm going to want to move around. Okay, so let's say I want to insert, I don't know, so I've got a while condition in here, and I'm going to move it along by using current next. And I'm also going to increase my counter. Okay, So what do I want to be doing? Basically, I want to be moving through the list until I get to the position where I want to be inserting. Yeah? So I want to, and when I've gotten to the position where I want to insert, then I want to exit out of this loop and actually perform the insertion. Okay? So what that means is I'm going to be okay, so remember we've got two options to traverse the list, and the two options are either we keep going until current is not equal to null, okay, and what current is not equal to null lets us do is it will move through the whole list including the last node, and you will end up standing over here at the null pointer, okay. The other option is to move until current next is not, I mean there's other options, but the two options that you most often use is to keep moving until current next is not equal to null. And what that means is that you will end up standing on the last node of the linked list. Which in our case, what that means is I can insert after this last node, but when I'm standing at null, I can no longer insert because I don't know where the heck to insert. So if this is saying if current is not equal to null, what that means is it means that I will traverse all the way through this linked list, and when I exit out of this while loop, I'm actually going to be standing at the null pointer. So I'm going to be standing over here, which means I can no longer insert anything because I'm now standing on a piece of memory that doesn't exist, okay? Now, that means when we exit out of this while loop, we're going to be standing at the null. Now, if I do something like this, where I'm checking that current next is not equal to null, that means that when I exit out of this loop, I am standing at the very last node, okay? Which means that it would allow me to insert at the tail of the list. So it means that I will actually be standing at this node over here because the next is equal to null. So when I exit out of this while loop, I'm standing on this node. I haven't moved past it. Yep. Okay. Great. So I don't want to be standing at null because it means I can't insert anything at the null position. So that's going to get awkward. Okay, so that means I want to keep going until I get to this. But now I should also, no, let's assume that the position is valid for now. And then we can insert when it's invalid. Okay, so when I exit out of here, I'm standing at the very last node unless it's interrupted before that, okay? So I've got a counter right now. Actually, no, what else do I need to check? Because right now I'm just moving through it. Why do you need the entire line 75? Line 75 has created the new node that I want to insert. That's why. Yeah, so I also need to check that my counter is not equal to the position, right? So as long as my counter is not equal to the position, then I keep going through this loop. Okay, so my counter is not equal to the position, and the position is coming from my input arguments into this function, okay? So, great. So I'm checking that the counter is not equal to the position, and I'm checking that I'm moving through the list, that I'm actually making my way through. So when I exit out of the while loop, I'm standing at the very last node, maybe, depending. And I also know that my counter is maybe equal to the position, right? Maybe, maybe not. We hope so. We can check whether that logic works. Yeah, so someone's picked up why that logic might not work. And I love that. So, okay, great. I've got an or here. Why do I need an and? What do we reckon? So right now an or, which means that whilst my linked list is still going, whilst I'm not at the last list, or my counter is not equal to the position. So someone thinks we should change it to and. I agree with that person, but no one's telling me why they think that. And maybe when we draw it out, we can have a look why that is, if it's not clear, because sometimes it's not clear. Okay, so I've exited out of the last, I'm standing at the last node, or my counter is equal to the position, right? Okay, great. So now I'm ready to do the actual insertion, which is fantastic. I'm assuming that I'm going to be ready to, so what I want to do now is, let's say I'm over here, right? So my node here, my current node, I want to connect to my new node, and my new node next has to be equal to the current next. Yeah? So what I'm going to do is I'm going to say, okay, my new node, the next, oh my gosh. Ah! Nope, one day I will type it correctly. So my new node next, so this bit here, so I'm drawing this arrow over here now, is going to be equal to current next. Yeah? And now I want, so I've done this connection here. Now I want to do this connection here, okay? So that means my current next now is going to be equal to the address of the new node. Now tell me, my lovely friends, why would I do them in this order? Why didn't I do current next is equal to new node, and then new node next is equal to current next? Why didn't I do that? Why did I do it in the order that I have done it in? What do we reckon? So why did I do these in the order that I did it in, and not in the opposite order? What do we reckon? Yeah, well done. So if I reverse the order, if I have current next is equal to new node, so if I do this first, then what will happen is this current next is going to be changed to the address of the new node, but what will happen is I will lose the address in the next to then go to this node. So what that means is I will lose this whole section of the list. My list is now going to be 1, 2, 7, and I'll lose the rest of it, right? So that's why we do this first, so that we don't lose the address to the rest of the list. Okay, great. So we're going to do this kind of magic. And then what should we do next? I think next let's do a return. What should we return from here? We said we're going to return a pointer to a struct node. So we're going to return the head of the list. Yeah, in case that head of the list has changed. Okay, great. Let's do it. Let's see what we have. Let's see what's going on. Let's go into main, and what we will do so we've got some sort of appending going on here. We've printed out the list. So now I'm going to call our new function, insert at. So I'm going to insert at position 2. So I'm going to call insert at, and I've forgotten which order I give things in, data position. So I'm going to do 7. Now I've already got a 7. Let's do 13 at position 2, and we're going to give it the head of the list. Okay, great. And we're going to see what happens next, and what it will return. Okay, and we might just want to print the list. And we want to print the list to see that it's giving us the right thing. All right, we've reached 30 minutes later. We've got something that we can compile. Let's compile. So remember, we compile the 2C files, and that's it. Great. And let's run them now. So we've got 716, and then I want to insert at position 2, and it started counting at 0. Anyway, it's inserted at 13, so that's good. It's inserting it at a position. Now tell me, how will I check whether it's working? What will I test it with now? What do we reckon we check? What do you reckon we check? We check now. What do we reckon? What would you do? Come on, folks, we've got this. We can do this. So the head is the address of the head of the list. So the head is a pointer. And all that means by that is that it's a variable that stores an address. It's not a node, but it's a pointer. What will I check now? Where will I check my insert? I've got it at position 2. Where would I check it now? Should we try it at position 1? See if that works. So how would I maybe break this? Okay, so it works if I change it to position 1. How else would I break it? Where would I try inserting to maybe for it to not work? Or where would I check that it's working? And where is the most dangerous place for it to, yep, let's do 0. Great. So we're going to check whether it works at position 0 at the head of the list. So let's do at the head of the list. Okay. That did not work, did it? That did not work at all. Okay. So, okay, that's not working for us. We can check why that is. Great. And what if I do it at position 5? Okay, so there's no position 5. What happens then? We haven't really thought about it. Okay, well, it did it at the end. Okay, great. And what happens if I did it at position 4 at the tail of the list, someone said, which is a great thing to check as well. Let's run it. It'll insert it at the tail. Okay. So let's see what the code actually does if we draw it up, and then we can see why it's not inserting properly, okay, in a few of the cases. So let's quickly do that before our little break, and that will allow us to see what's going on. Okay, how is everyone feeling? How are the feels? How are the vibes? It feels like everyone is slowly cooking, not in a good way, not in a way that would be a nice way to cook. So I hope that's not the case. I keep reassuring you, it gets better, it's amazing. I hope that you don't just feel like yeah. Okay. Okay, let's go through it and let's draw it up. Okay, how does that sound? Why didn't it update here? Let's refresh this. That's better. Okay, so we're going to go through this function and we're going to draw it, and we're going to see what's going on. Okay, great. I have a function. The function is called insert at. I'm going to, well, you're not going to see anything I'm writing now. I'm going to call this function, and I'm going to give it 3 things. The 3 things I'm giving it is some data. So I've given it 13 in that. I'm going to give it the position that I want to insert it to. So let's do it with the middle of the pack. We'll do it with 2. And I'm going to give it the head of the list. Okay. So in this case, what this means is that this 13 is this data over here. This 2 over here is this position in the code. And this head over here is this head over here. So this is the head of the list that I pass it. So that means it's gotten 3 arguments, okay? Okay, great. Then we go through and we do line 75. So line 75, we'll go to the right side and we'll do it first. The right side of this is calling our function create node. So it's calling a different function, and the function that it's calling is called create node. And this function is given some data, and that data is coming from here. So this data over here is the same data that's in here, which means that it's giving it 13, and it's also giving it null. Okay, I am being sent off to my create data. So I will go to this, create node. I've come to this function create node from this function call, and I'm now going to go into this function. So the first thing I'm going to do is I'm going to malloc size of a struct node. What that means is I'm going to malloc enough space for a node, and that node is going to be built up of two things. It's going to have some data, and it's going to have a pointer to the next thing. Okay, so I've malloc some space for it, and now I'm going to assign the return of malloc. I'm going to assign it to this pointer new node. So that means that I've just assigned the memory address that this is sitting at to new node. And let's pretend the address of this is 0xa. Okay, so this new node was created, it's got an address, and then I'm assigning it to this new node in here. Great. So my new node is equal to the address of this new node that I've created. I'm now going to access new node, so dereference new node, which means go to the address of new node, go in here and access the data element of it. So access the data element and then assign it whatever data was sent with this. So I've sent it 13, which means that now this is going to be equal to 13. The next line, again, dereference this address. So go to the whatever is sitting at this address, okay? And then go into the next part of it. So go into the next component and assign to it whatever was sitting inside next. So in this case, it's the null. So we're just going to go here and we're going to assign the null to it. Great. So it's now null. And we've now got that. So now this node has the assigned of 13 and null that we send it with, and we now return the address of the new node. So what happens now is we go back to the function where the call was made from. This create node has returned the address of the new node, and that new node is now assigned to this new node. So I'm going to switch colors to, so remember what I said, this new node here is not the same as the new node that is inside my insert add function. So the new node is now being assigned the address that was returned to it, which is 0xa. Okay, what that means is we now have a beautiful node in here ready to be inserted. Okay, and if we were to look at our list here, was right now composed of three things. Okay, so the list that was here looks like, that was a terrible color choice. The list right now looks like this. So it's got a 7, it's got a 1, and it's got a 6. That's from our main function, right? That's what we have. And now we want to insert this one. Okay, great. What's going on? Why are people stressed over here? Okay, I don't know what's going on in the lecture chat for now, so I'm going to keep going here. Okay, so the first thing we do over here is we're going to check if the list is empty. Is the list empty? No, I've got 3 things in the list, which means that we do not go into this if statement, and instead we move into the else, okay? So in the else, we've got a counter, and we set it to equal to 1. So I've got a new variable, and that variable is counter, and that variable is equal to 1. I then create a pointer current, and this pointer current is given the address of my head, okay? So what that means is this is the head of the list that was sent it to. So this is now also the current. Okay, so the current is sitting at the beginning of the list. Great. So if these had addresses, again, these are pretend addresses. So I'm going to just, okay, B, C, D as their addresses. Okay, that means my current is going to be equal to B right now. Great. Moving into my while statement. My while statement says, whilst current next is not equal to null. Okay, so my current is over here. So I'm going to check what's inside next. Well, there's something there because it's pointing to a different node. So this is all good. It's not equal to null. And my counter is not equal to position. So my position was given over here. Position is 2. My counter is 1, which means that this is also good. So I'm going to keep going. I'm going to increase the counter by 1. And I'm going to move the current to current next, which means I'm going to go to this address. And my current is now going to go into here. Great. Okay. And I will check again. Is current next not equal to null? No, it's not, because that thing has another node there. And my counter is not equal to position. So my counter is equal to 2 and my position is equal to 2, which means that this is true. Okay. Which means that I'm going to exit out of here. So I'm either standing at counter is equal to position at this point in time, or I'm standing at the very end of the list. So in the current situation, I'm not at the end of the list, but I'm standing where counter is equal to position. So it means I want to insert. So what I do is I get my current next. So I go into this current next thing here. And what I do is I assign it to new node next. So that means my new node next over here gets a current next. So current next is pointing to D. So that means I've got my new node next. So is going to be the current next. So what I've done is I've drawn this connection. Okay. So now I want to draw from 1 to 13 connection. So here I'll go to current next and I'll get my new node. So current next inside here is going to get the address of the new node. So it's going to go into 0xa. And then I'll return the head again. So the head has not changed because I haven't inserted anything at the head. Okay. How does that feel? Can we please do a little poll? How does that feel? How does it feel? And I'll introduce a little bit there. Sorry, I'll read the chat for a second. Why even the position is out of boundary? The new node will sit end of... Okay, I understand what you're asking. So if position was 5, right? What that meant is, okay, my counter increased here, my counter increased here. So if, when it was somewhere here, I did 5, okay? So let's say my position was 5. When I went through here, because my current next was not equal to null, right? And my counter was just, so, okay, I understand what you're saying. So what happened was I have 3 nodes, yeah? And when I did position 5 over here, my current next was equal to null because I'd gotten to the end of the list and this was still not true, right? So when I exited out of here, I was just standing at the last node and then I just inserted. I didn't check whether it was because my counter is equal to position. So this code still needs a little bit of fixing, right? So that's why it just inserted it in. I look so weird on the camera. Sideways, sorry. I move my hands around a lot. Okay. Okay, so we're getting how we're feeling. Okay, it's going okay. There's still a little confusion, which is okay. We're going to try deleting things after the break, and then we're going to see where we're at. And then don't worry, next week we can still do more, right? So please don't stress. And as you do your assignment, it will become more clear as well. And there's things that we can do here that we can still fix this code, okay? a lot, like it's not perfect, right? Now, what was this? Can you explain new node next is equal to current next and line underneath this? Okay, this bit here. So this bit here is where I make these two connections, okay? So what I've done is I've created, so I'm just going to draw it for you over here just because it's so messy right now. So and I'll do it in a different color. So let's say this is my new node, and my new node has the number 13 and it's null. And then I know that I'm going to be inserting, this is my current node here. So this is my current. This is my new node. And my current is 1 and then next, and it points to 6 and then null. So if this node over here is my current node, okay, that means that this over here is my current next node. Okay, so what I'm doing in these two lines is I'm going, okay, I would like to go into grab me the address sitting inside current next right now, which means that I will dereference this current and I will grab the address sitting in here. And what I will do then is I will assign it to new node, whatever's in next. So dereference my new node, go into next, and assign this address to here. So what that means I'm doing is I'm saying this is what I'm doing now, right? So I'm directing it, whatever was next here, I'm now putting it in there so that it does that movement. And then in the next line, I grab the address of the new node and I put it inside current next. So instead of having the address of this one here, it's now got the address of the new node. So now it's going to be going like this. So basically what those two lines of code are doing is they're actually allowing me to insert the node in between two nodes, right? I am changing the connections of the nodes to allow for this node to slot in. Is that better? Yeah, so in this current situation, the meaning of position is clearly a little bit ambiguous, right? Do you start counting at 1 or do you start counting at 0? So that's a very good point, absolutely. And where I think I just wanted for you to see how to insert in between two nodes, but you will never get a question that's so ambiguous in a spec, right? Or in an exam or anything like that, right? So at this point, we're inserting after position, really, not at position. This should really be called insert after. Or we can change it to start counting from 0, and that will shift us backwards 1, okay? And then we can also, if we do that, if we start our counter at 0, then here we can also check what happens if we want to insert at position 0. Because if we want to insert at position 0, it means we would change the head as well. Yeah? So we could check here if head is equal to null, or position is equal to 0, or position is equal to 0. And that will change the head of the node, yeah, if we do that very first position. Because in both of these cases, you're inserting at the head. Here, it's not going to work actually if the list is empty, this will work, okay? But if this position is 0, then this is not going to work, right? You're just going to return this new node, but you're going to lose the whole rest of this list. So should we fix it? Do you have like 5 more minutes before I take a little break? Should we fix it? Yeah, let's fix it quickly. Okay, so in this case over here, if head is equal to null, it means I've inserted into an empty list. I don't have a linked list. So all I need to do is return the address of this new node, right? Because that's all I need. I only have one node in there, and that's the node. That's the head of the list. However, if position is equal to 0 and I actually have a list, I just want to insert, so if I have this list here and I just want to insert at the beginning of the list, if I just return the new node, then what I'm doing is I have no connections. That new node is still going to have null, and that means that all you will have over there is going to be just that one node and no linked list. So this is what's going to happen. I'll show you. So if we go to main and I'll insert it at position 0, then it's not going to work. It's just going to have that 13 and nothing else, because it's not going to have the address. Or in fact, it's going to have nothing, and I don't know why it's doing that. That shouldn't be doing that. Oh, I know why it's doing that. So the reason it's doing that, the list remains unchanged, is because we're inserting at the head of the list, which means the head of the list has changed, yeah? But we're not actually assigning that address to anything. And that's why a lot of the issues were also happening. So let's see what happens now. Okay, so this is what I mean, right? So what happens now is the head of the list has changed, but I haven't actually attached it to the rest of the little train. I haven't attached it to the rest of the list. So what I need to do is I need to modify this so that the very first node now connects to the rest of the list. Yeah? Okay, so if that's the case, so what I want to do here is, okay, I want to, my new node next. So my new node, remember, is going to be the head of the list, and then the next of the new node is going to be the head of the list that was sent here. So what I'm doing is I'm taking this new node and saying it, the next should point to the head of the list, to the address of the first node that used to be. Yeah? Great. And then I'm going to say the head is going to be equal to the new node. And that's it. Okay, let's see what happens now. Compile it and let's run it. Okay, and now we have the node inserted properly into position 0. Yeah? And I could absolutely do another else for position is equal to 0. I could do that. Yeah. You don't get new node next head, okay? Of course. So let me draw it for you. No problem. Okay, so this is what it would look like. So I have a list, okay? And my list looks like this right now. 7, 1, 6. And I'll have addresses A, B, C. So this is to B, this is to C, this is to null. So like this. And this one here is the head of the list right now. And you can't see anything because I'm drawing like a crazy person. Okay, that is the head of the list. Okay, so what happens here is I want to insert at position 0, and I want to insert this new node, and this new node is just an empty node. Let's say the address is D. I want to insert it at the head of this list, so I want to insert it over here. Yeah? Which means that what I want to do is I want to insert it in, and that means I need to create this connection over here. So I want this next to point to the address of this, okay? And the address of this first node is stored inside head. So what I'm doing over here is I'm taking the address of the head, so I'm taking this address, and I'm putting it, assigning it into the new node. This is my new node here, into the next part here. So I'm putting it inside here, and what that means now is that my list will start with 13, then it will go to 7, then it will go to 1, then it will go to 6. And because then I reassign my new node address is now the head. So the head is now going to be at the address of D, whereas before it was the address of A. Yeah, does that make sense? The head does not represent all lists. What it does is it represents the address of the first node. So it only stores an address of one node, and that node is the first thing in the list. And to get to the rest of the elements in the list, I need to know where the first thing is, because from the first, I can go to the second, to the third, to the fourth, and all the way to the end. Okay. How does that feel? Does that feel okay? I know there's like a... Okay, let's have a 2-minute break. We'll have a very short break and then we'll look at deleting things. And you know, that should bring you some joy because you're freeing memory, you're deleting nodes. Finally. Okay, so let's have a 2-minute break. All right, it's not clear what we want. Do we want Kahoot? Do we not want Kahoot? 55 to 45. It's quite a tight squeeze there. Can a few more people take a vote? There's 45 votes. We can absolutely make a node hold more than one piece of data. Yeah, you can add, it can hold a string, it can hold a data, it can hold another struct, it can hold anything, right? As long as it has that pointer to the next node, that's what makes it a linked list. Okay. It's all very close over here for whether we're, and someone said that they can't see the code. Can you not see the code? Ugh. Feels like evening. Okay, I think we keep pushing. It's a tight vote. Okay. Okay. Oh, winter is coming. I miss Game of Thrones. Okay. Let's keep going. Let's look at how to delete nodes. Deleting. Okay, so to delete nodes, and remember we will we will rehash all of this again. Okay, so don't worry, right? I don't expect you to understand everything from the get-go after 2 hours. I mean, that would be crazy. It definitely takes a lot longer than that to understand linked lists, and to get better at them, you just need to keep practicing with them, as with everything in computing as well. You need a lot of practice. Okay, so where can we delete in the linked list? Okay, so where can we delete? We can delete nowhere, right? If it's an empty linked list, well, you're not going to need to delete anything because there's nothing to delete. Great. We might need to delete at the head of the list. And if we're deleting something at the head of the list, that means the head of the list is going to change, because we're going to need the next node to now be the head of the list, because the first node is now gone. Okay? We might delete between any two nodes that actually exist. So then we will need to fix up the connection between those two nodes. And we might delete the very last thing in the list, which I reckon is the very easiest thing to delete, right? Because then you only have to modify one thing. But you have to think about it. So let's look at it in code. So if we look at it in code and we're deleting anywhere, nowhere, because the list is empty, again, we use the familiar structure where we have a pointer called current, and we assign that pointer the address of head, okay? What that means is I don't want to modify the head of the list. I'm just going to manipulate stuff with the current pointer. Okay, if current is equal to null, which means that the list is empty, there's nothing there, then I'm going to return null, right? I'm going to just return a nothing out. There is nothing there. Nothing we can do. Great. Deleting if there's only one thing in the list. If there is only one thing in the list, then what happens is I've got the head of the list. It's storing the address of my very first, and in this case, only node. Okay. So one node, it's got an address that's stored in the head. What I do is I'm going to delete this node. So I'm going to free the memory that is allocated to this node. So I'm going to free the head of the list, and then I'm going to move on with my life. Things are good. Now, deleting at the head of the list with other items in the list, right? So I've got more than one item in the list, okay? again, I've got my current, I assigned it the address of the head, and then I'm going to move along. So if my head is the current, which is what I've assigned over here, that means my current next is going to be over here. Now I want to delete the head of the list. I want to delete this node here, the very first node, and that means that I want this node now to be the head of the list. So what I do is I'm going to get a new head of the list, and that head is going to be, and before I free the head of the list, I need to assign my current next into the new head, because if I free the head first, then I've lost the rest of the list, okay? So the order really does matter. So the first thing I do is I assign my new head the current next, and then I free the head of the list, okay? So then I free the current and I move on with my life. Okay, now my camera is in the way of seeing what's going on. So let me, nope, that's not it. Let me move my camera. Here we are. Whee! Okay, move my camera. So let's say I've got deleting in the middle of two nodes. Okay, so let's say I'm going to delete this one over here. Okay, so again, I'm going to assign the head of the list to my current pointer. So I'm going to move it on up here, and then I'm going to move along until I find the right node to delete. So for example, I want to delete the node with data is equal to 3. Okay, so if I want to delete this node with data 3, then I can't stop at this node, because all I have access to then is the next one, but not the one before it, right? And my connection is going to need to be from the one before it to the one after it. So that means I'm going to need to stop at the one before it. So I'm going to be checking that current next is not equal to the value that I want, because that's going to allow me to stop at the node previous to the node that I want to delete. Okay, so current next data is not equal to 3. So what that means is I'm dereferencing current, so going to the address in next of data. So I'm checking this value here. So if current next data is not equal to 3, I'm going to move my current pointer along. Okay, now I found it is equal to 3, which means that what I want to do is I want to go from this one over to this one. So my new next is going to be current next, next. Yeah, so you can have as many nexts as you want, but this is just a way to kind of make you see what's going on. And then I'm going to free that current next. So I'm going to free this one, and this connection is going to be the one that exists. Okay, great. So my current next is going to be the new next, and I'm ready to keep going. And then what happens if I need to delete at the tail? Okay, if I need to delete at the tail, then again, I set my current to the head of the list, and then I want to move until I get to the end of the list. But to get to the end of the list again, I want to be standing before the tail, right? So I want to be standing at this one to delete the tail, because I want to know what the previous one is. Although in this case, I don't even really need to do that. But anyway, okay, let's do that. So I would be checking current next is not equal to null. So I'm skipping one over, and I'm moving it along, and then I free the tail when that's okay, and my current next is going to be pointing to null. So I point my current next to null. And the reason I don't just free my tail is because I don't want to have this address in here that is kind of going to nowhere. That needs to point to null, right? Because if I free this piece of memory that is sitting at this address, and then I try and access it and it still has that piece of memory, that's going to cause me some serious problems. Okay, so kind of think about it methodically to start with. And the methodic is find the previous node to the node that you're trying to delete, okay? Because in the way that we're doing linked lists right now, we're only moving forward in a linked list. So you only know what's the next node in the linked list. You do not see what's the previous one. Although you can keep track of the previous node as well. And we will kind of do that next week, where we will see whether you prefer that method to kind of always going next, or however many nexts. Okay, great. So always find that node, change the next of the previous node, free the node that's to be deleted, and then think about what happens, at the head, nothing, when there's only one item in the list, and when you delete the tail of the list, and so on and so forth. Okay, so let's look at some code. Yes! Any questions in the chat so far? Questions so far? Okay, everyone's chilling. Let's do some functions. Okay, let's do this next function. And let's do this node 2. I can see the chat. Yeah, so if you're deleting at the 3rd position, you want to find the previous to that one and stop there, because you want to be able to connect that previous node over. Okay, great. So we want to delete, what should we do first? Should we delete a value? Let's do delete value, because then that will allow us to see stopping previously, and then we can do something else. Okay, so function to delete a node with a particular value. Does that sound good? Let's think about what would be the inputs into it and what would be the outputs out of it. Okay, so what will be the input if I'm deleting from a list and I'm deleting a certain value from that list? What would be the inputs into that function? Yeah, so what I want to give it is I want to give it the value that I want to delete. So my int value. And the other thing I want to give it is the head of the list in which I want to delete. So that means I'm giving it a struct node pointer head. And what will be the output of the list? Oh, I'm now in the wrong place again. Sorry. Let me move the camera. Okay, camera moved. Yeah, excellent. So I'm going to output the new head of the list in case I've deleted the value at the head of the list, okay? So mostly with our linked list functions, especially insertion, deletion, I'm mostly always going to give back output potentially the new head, because I can't do anything else if I need to change the head of the list. If I need to change the head of the list, that means the head has changed, and that means that I will lose my whole list. Okay, so whilst it seems like it might be void, think about what happens if I need to delete the head of the list. Then the head of the list will change, and that means I'm going to give it the head of the list. So standard practice, the new head of the list, just in case. Okay, we always got to be careful. And that means I'm returning a struct node pointer to the head of the list. Okay. Exactly. So it could be void if I'm not deleting anything. If I don't delete at the head of the list. But just in case I delete at the head of the list, I need to give it the new head. Okay? So that means my definition is struct node, delete value is the name of the function, and we're giving it some value to delete, and we're also giving it a head of the list that we want to delete in. Okay, I'll save that, and let's go over here and let's get ready to do some deletion. Okay, great. Amazing. Let's do it. And if we have time, let's do it both ways. Why not? I'll do previous as well. Do you want to learn how to do previous instead of current, next? What do you prefer? What do you reckon? What do you think would be less confusing. I think the current next gets really confusing because there's just a lot of nexts and you got to keep accessing. So do you want to do it with previous to start with, and so that you can see how that works? Okay, so I guess there's only two people. They think previous is the way to do it, so let's do it. So what I'm saying here is, let's say I've got a list, and that list has okay, this list has a whole bunch of things in it, right? So what I'm going to do now is I'm going to set two things. I'm going to set a previous and a current, okay? So I'm going to keep track of my previous at all times, which means I don't have to do current, next, blah, blah, blah. So it means so usually we have this struct node, no, not node, my God, no, node current. Okay, so usually, and we set that to head, yeah? So what that means for us is that this is the head of the list. It is also now the current node. Now, if this over here is the head of the list and the current node, because I've set the current to the head of the list, then what do you think in this case, if I'm keeping track of my previous node, what do you think would be my previous node set to? So if this is my current, where will be the previous node? Yeah, excellent. So what it means is my previous, if my current is over here, my previous is sitting over here in space, and that means the previous is actually nothing right now. The previous is null. Yeah? So to start with, my previous is null and my current is equal to the head. Okay, so now I want to have a loop where I'm looking for a particular value of a node that I want to delete. Okay, so I'm going to loop until I find the value that I want to delete. And in the loop, I'm going to update both my current and my previous nodes, because that will allow me to keep track of what's going on. Okay, great. So how will I loop until I find the value that I want to delete? What do we think? So I'm going to be looking for the current data, and I want it to not equal to the value, right? Because I'm going to keep looping while that happens. Otherwise, I'm going to exit out of the loop. Because when I exit out of it, I want to know what's going on. Okay, now, what else should I be checking for? So it's all well and good. I'm going to check that the current is not equal to value. What happens if I want to delete a node with value 7? What happens in this case? I want to delete value 7. What's going to happen in this loop? Yeah, excellent. I'm going to keep going, right? I'm going to come out. It's going to keep going into memory that doesn't exist because I don't have a value of 7 in this list right now in the example, which means that I will keep moving through and I will start accessing memory that doesn't exist. So I will completely and utterly crash out. So what I want to be doing is I want to also be checking that my current is not equal to null. So that means that I've gone to the last node because I want to check the last node, okay? So in this case, I'm going to check whether, and I'll show you why, okay? When I draw it up, I'll show you why it's not current next is not equal to null, why it's current is not equal to null. So I'm checking two things. One, I'm checking that I haven't gone past the end of the list. So need to also check that you are not going past the end of the list. And you're doing that with current is not equal to null, okay? That allows you to go through your whole list, accessing every single thing in that list. And you're also checking that the data is not equal to the value that you want to delete, okay? So as long as those two are okay, then what you want to be doing is you're going to be moving your nodes. So previous is going to be equal to current, and current is going to be equal to current next. So what you're doing here is you're moving previous to current, and current is going to be current next. So each time you're going to be moving both of those nodes over and over and over and over again. It means that when you exit out of this loop, and when you exit out of this loop, either one of these conditions has been met, or both of those conditions, okay? So either one, you have gone through the whole list, okay? So you are now at null. Yeah? Or the second thing that might be true is that your current data is what you want deleted. Yeah? Okay, great. So if I've gone through the whole list, which means that I'm standing at the end of the list. So if my current is not equal to null, okay, that means that I have kind of removed this chance from happening, right? So if my current is not equal to null, that means that this must be true. That current data is what I want deleted. Okay, great. Then I want to delete a node, okay? So let's say I want to delete a node with 4 in it, okay? That means let's delete 5. So let's look at what it would look like. So if I want to delete the node with 5, for example, in the example, I want to get rid of this node. That means what I want to happen is this is going to be my current. This is going to be my previous node. That's how I'm moving them along in here in this while loop. So what I want to be doing is my previous next, I want it to point to the current next, okay, before I delete it, because I want this address to now be pointing like this. And then I can delete that node, okay? So that means that I will do previous next is going to be equal to current next. So what that means is I've redrawn from here to here. So I'm ready to free this current now, okay? Got a semicolon. Now, you all know that I love writing with bugs to start with so that you can see what goes wrong, but also so that you're not scared to make mistakes, right? It's okay to make mistakes in code and to fix them as you go. And then we're going to free the current, which means that we're going to do that cross and we're going to delete that node. Yeah? Does that sound good? Let's give it a whirl, okay? So let's go in here, and that was insertion, printing the list. Let's go in here, and I'm now going to delete value. Now our list over here is 13716. So the first thing I'm going to do is I'm going to delete value of 1, okay? So we can see the plain thing in the middle, nothing, no edges, right? So it's all easy, okay? Great question. What if two nodes have the same data value? Right now, this will delete the first node with that, and then it will move on, but we can redo. You absolutely would need to take care of that. Good question. Okay. let's have a look what happens. So I'm deleting number 1. So I want to delete this node over here. So let me clear this up and let's compile it. Okay, amazing. Somewhere I've line 122. I've forgotten to return something, of course. Okay, we're going to return the head. Note that we haven't taken care here of anything to do with the head yet. Okay, let's try this again. All right, it's compiling now, and let's run it. Should have printed a new line, but over here you can see that it deleted the one, no problem. Okay, let me do a new line here as well, and I'll run it again just so that you can see. Okay, so this is okay. My first list, my list after I've inserted, and then my list after I deleted the one. Okay. Someone has asked an excellent question. What if the previous is equal to null? What a fantastic question. That is exactly what I'm going to demonstrate now. So what happens if I'm deleting value over here, the very first node? And in our case, what happens if I try and delete 13? So what happens if I try and delete the head of the list? So let's compile and let's see what happens. And our code right now is not coping with it, right? That's because right now it's trying to delete it and you're getting this runtime error. And the runtime error is accessing a field via a null pointer. So what that means is previous is equal to null. So when you try and go into previous next, you're dereferencing a null pointer, right? And that means that you cannot do that, okay? No go. So we need to take care of that now, okay? Great. So if current is not equal to null, in here, I'm also going to check if previous is equal to null. What that means is that I'm deleting at the head of the list. I'm deleting the very first element, okay? And that means that I'm going to be a bit naughty. So this is going to become an else in here. Ooh, what did I do there? And then I'll draw it up after this, okay? I'll draw it up and then we can move on with our lives. So if I've deleted this first node here, then what I want to do is I want my head to be pointing to whatever was inside here, the head next. Yeah? Does that make sense? So what I'm going to do here is I'm going to say head is equal to head next. So what I've just done is I have made the head equal to this next thing here. And then up here, I'm going to free the current. So I'm going to still free this piece of memory that was allocated. Okay. So let's see what happens now. If we run the code now. So let's compile it. Let's clear it from the error and let's run it. Okay. And now we can delete at the head. No problem. Fantastic. Okay. Great. Now, what happens if the list, how are we going for time? 3:44. We're still going good. 4 more minutes. Kind of lost? Okay, then it's time to draw it up and go through it. Okay, let's draw it up. Okay, I'm going to get rid of all of this and we're going to go through the code with the drawing. That always helps to get back to life. Does that sound good? And then we can talk about the next possible case. Okay. All right, so in here, I'm sending some code, delete value, and I'm giving it some values. So I'm calling my function, and I'm calling the function delete value, and I want to delete value. Let's go here. We're deleting value. Should we do in the middle first? Let's do value 7, and the list looks like this. 13, 7, 1, 6. So I'm deleting 7 and I'm giving it the head of the list. Okay. Yeah, sorry, I was trying to draw the, I wanted to get the thing first. That's why you couldn't see it. Okay, great. So I've got this, why is that? I'm sending it delete value and I'm giving it 7 head, and I've got this thing here. Okay, this over here is the head of the list. Okay, so it's set to this node right now. So I go into this function. Okay, this over here is the value, and this over here is the head of the list. So I'm giving it this address here, and if it helps, I'll just do little A, B, C, D. So that means that this right now is equal to A, right? Okay, great. So what I'm doing now is I'm setting a few things in here. So I'm struct node current is equal to head. So what that means is my current node is equal to the head node. So it's A, and that means it's sitting over here. And then I say my previous node is equal to null because it's sitting over here, right? It's previous to my current, and that means it's right now in space, right? That doesn't exist right now. Okay, great. Next line of code. 2 things. Whilst current is not equal to null, okay, great. Current is not equal to null because it's got an address in there. And current data, so my data inside my current is not equal to the value. And the value is 7, okay? So it's not equal to it. Okay, so 13, 7, 1, and 6 is the data that's stored inside the nodes. Okay, so that means that all of these are not equal, they're all true. So I go in here and I take my current and I assign the address of the current to the previous, which means that the address of the current, which is A, is going to go in the previous, and that means my previous now moves to here. Okay, and then my current is going to go to current next. So my current next, I go inside here, I dereference whatever's in current, which is A, I dereference the next part of it, and I move my current over to that address. So I assign it to over here. Great. So current is now here, previous is now here. And I check again, is current not equal to null? And current is now over here. Current is not equal to null because it's got an address in it. Great. And current data is not equal to value. I check my current data and it is equal to value, which means I exit out of this loop. So I could have exited out for 2 reasons. This was not true. That's not the reason I exited out of the loop. Okay, so current is not equal to null. This is true. So I've checked that I've exited out for the right reason. And now what I'm going to check is previous equal to null. And this is relevant if I was deleting at the head. So we'll do the next case that I draw at the head of the list. So is previous equal to null? No, it's not. Previous has an address. So I'm going to go into the else. And what I will do is I'll go into my current next. So I'll grab this address over here. And I'm going to assign it to previous next. So I'm going to take this address, so this address which was C, and I'm going to place it into my previous next here. So what that means is I've done this connection over here. And then I'm going to free the current. So I'm going to free the memory at B. So I'm going to free this bit of memory. I'm going to deallocate it, okay? Null is nothing, okay? There's no memory there. It's an empty chunk of memory, right? There's nothing sitting in that piece of memory. It's null. Zero, zilch, nothing. Okay, and that's it. And then I return the head of the list, so I return this head. Okay, so what happens if the value that I want to delete is done so much messy drawing that now I'm like, let's say we want to delete 13. Okay, so 13, 7, 1, 6. And this is the head. And now I want to delete the value 13. And I'm giving it the head of the list. Okay, so this is my value. And this is the head of the list over here. Okay, so let's have a look what happens now. Okay, great. So again, I'll go in here and I'll set my current to the head of the list. So that means I've got my current, and my current is going to be set to the head of the list. So let's, for example, okay, these are completely made up addresses. This is A, this is B, this is C, and this is D. Okay, so the head is equal to A, and this next, I'll fill them in based on that. So this one is going to be pointing to B, this one's pointing to C, this one's pointing to D, and then that one's pointing to null. So that means now what happens is that my current is being set to the address inside head, which is set to the address of the head. And my previous, because my current is currently over here, my previous is previous to it. So it's sitting somewhere here, and it's equal to null because it's pointing to nothing, right? There's no memory yet that I'm using there, and I haven't moved it yet to kind of account for that. So my previous is sitting nowhere yet. Okay, I'll go in here into the while loop and I'm going to check. Whilst current is not equal to null. Yep, current is not equal to null because it's got an address in it. And my current data is not equal to value. Aha. So my current data over here is equal to the value that I want to delete. Okay, which means that I will exit out of here without doing any of this movement, right? And when I exit out, I check. If current is not equal to null, so that is the check to make sure that I'm not trying to delete after the end of the list, okay? Okay, then I go in here and I say, is previous equal to null? It is equal to null. My previous is over here, and it is very much equal to null, okay? So that means that I can't access the previous next and connect it up to here because there's nothing to access. You can't access the null pointer. So what I do instead is I'll say head is equal to head next. What that means is if I want to delete this node, then I want this to be the head. So this is the head of the list. I'm going to dereference the address of the head of the list inside next, and I'm going to set that to be the new head. So what I'm going to do is I'm going to make this to be the new head. So now the head is pointing to this node over here. And then I will come out and I will free the current, which is this node. So I will get rid of this node and then I will move on with my life. Just like I promised, you all will move on with your life. I hope you're not crying on the inside. I hope you're just enjoying the beautiful drawings. Okay, what happens if I wanted to delete the 1? Okay, what happens if I wanted to delete the 1? Okay, if I wanted to delete the 1, okay, so now let's do the 1 quickly and then we're going to call it a day. So let's say we're deleting the 1, means we'll want to delete this node over here just so that you can see the movement, okay? So again, we start by setting the head to the current, So my current is over here, and it's the same as the head, and my previous is equal to null. Yeah. So it's in off in here. It's still nothing. Okay. Great. So I'm going to now go and I'm going to go into my while loop. Current is not equal to null. No, it's not. It's got an address saved in it, so that's good. And current data is not equal to value. If I go into current data and check against the value, they're not equal to each other either. So I'm going to go in here and I'm going to assign my current to my previous, which means that my previous is going to move up to here. So previous is going to get the value of the current. And then my current is going to get the value of current next. So current is at A. I'm going to access whatever's sitting here and I'm going to change it to current next. And that means that my current has moved on to the next node at B. And then I go and check again. Is current not equal to null? Nope, it's got an address, so I'm good here. And is current data over here equals to the value? No, it's not. Great. So that means I'm going to make the movement again. So I'm going to take my current and I'm going to assign it to the previous. So I'll take this current, assign it to the previous over here, which means that my previous has now moved over here. And then the next line over here, I'm going to take my current next. So my current's at B and my next is equal to C. And then I'm going to assign it to current. So I'm going to make this C, which means that this current is now pointing to the next node over here. Then I will go through and I'll check again. Is current not equal to null? No, it's not. I'm all good. There's an address there. And current data is not equal to value. So I'll check my current data. Aha, it is equal to the value. Great. So I'm going to break out of the loop and I'm going to go down here and I'm going to check whether I'm not gone past the end of the list. So I'm going to check that current is not equal to null because that would mean I'm standing over here and I can't do anything. Okay, great. Current is not equal to null because it's got a value in it, an address. So now I'm going to check is previous equal to null. No, previous has an address as well. So I'm going to move to else. And what I'm going to do now, I want to delete this node, which means I want to connect my previous node to it, to the one next to it. So what I'll do is I'll take whatever is sitting in current next. So my current is here. I'll take the current next, so the D, and I'm going to assign it to previous next. So previous is over here, so I'm going to assign it over here. Yeah? So that means that this node here is now pointing to this node, and then I'm going to free the current, which means I'm going to get rid of it. I'm going to deallocate the memory that it had to it. So it's no longer in my linked list. I've just tossed it out of the linked list. And then I'm going to return the head of the list, which is at address A. Okay, how does that feel? Can we have a little poll to finish off with? How do we all feel? Are we cooked? Are we good? Did that help? How are we feeling? What are we feeling? What are the vibes? Yeah, you free the node. But before you free the node, it's really important to assign all the connections first, because once you free and deallocate that piece of memory that you've mallocked, it's all over, right? You can't find anything. Basically, the free goes together with the malloc. If you have mallocked a node, that means you've allocated some memory, and then you're going to free it with the free. Oh, group hug. I wish I could give a group hug. Group therapy. You know, you've got each other. There's so many of you. Come on. That's the therapy. Okay, I've got it up for feedback. Just let me know, because I know some of you don't want to write in the chat, but just let me know if you want me to slow down a little bit. You want to know how much more difficult 1521 will be? I don't think it's a good idea to tell you in this course. You shall find out. But it's still as fun. It all needs more practice, absolutely. But it's all so much fun. You know, you're getting such an intimate look at what the computer can do and how much the computer does for you. It's nothing to stress about, I promise. Well, a little stress is maybe helpful, I don't know. Yeah. I hope you have a lovely week ahead. I look forward to being back in person next week and seeing you all in the theatre. Hopefully, no one will be falling asleep because we're going to be doing linked lists. Um, we'll do a lot more practice of these two things, okay? Because we still have 3 nodes that we've malloc that we haven't given. You know, we're going to do deleting the whole list. We're going to do different types of deletions and maybe another insertion. Who knows? But I hope you have a lovely week ahead, and I'll see you guys next week. Bye.